It's a pleasure to welcome Nicolas, who's going to give us the last of his Eisenstein series lectures on Sczech cocycles and hyperplane arrangements. So, voilà.
Thank you. So yes, that's the last one. And at last, I will discuss some arithmetic things, and in fact, I will discuss the Eisenstein series. This Eisenstein series, as I already said in my last two lectures, will be associated to the differential form phi and psi that we have already considered. But now I will restrict this form to the symmetric spaces associated to SL and R. So now, in fact, I will denote by S plus. So contrary to what happened before, S plus will be GLNR plus over SON. And now X, so in this talk, will be S plus over the positive reals, which is the same as the symmetric space associated to SLNR. X is a classifying space. I mean, is a universal cover for of a classifying space for any torsion-free discrete subgroup of SL and Z. So you see the relation with E gamma. Okay, so that will be, of course. So let me just say it. X gamma is homotopy equivalent to B gamma if gamma is a finite index torsion-free subgroup. So this is quite natural to compute equivariant cohomology using this space. And as I said, we will globalize the construction today. Globalize the construction, the preceding construction, using psi as Archimedean test function. I will explain what it means, and this gives an Eisenstein series which I will denote I psi S. So it depends on a complex parameter S, and the value at 0, and should think of it as average of eta by a lattice, and this form will give us our preferred gamma equivariant class that I have discussed in the first lecture. So
this is a real analytic Eisenstein series.
This is a real, this is a real analytic Eisenstein series, but it's not a standard Eisenstein series because it will live on the bundle, on the CN bundle. You will see. But if you pull back by a torsion section, then you get a real analytic Eisenstein series. Yeah. So to really insist on this Archimedean test function, I will work adelically today to distinguish this Archimedean test function from the finite test function. So it's this has some drawback because there is somewhat machinery to enter, but I hope this will explain why I make a distinction between Archimedean and finite test function. So let me say a few words on adelic quotient and hopefully try to help you to go from adelic quotient to usual quotient. So A will denote the adhers of Q, and the standard notation, if you take GLN to be the standard GLN group over Q, you put this I denote this the double quotient GLN Q, GLN A, and here SON, and the center of GLN plus. So this is just the positive reals embed in the center. So we denote. So it's a standard notation to denote it like that, and you should think of it. It's a bit false what I will say, but you should think of it as something like the quotient x over gamma, but take the limit over all congruent subgroup gamma in SLNZ. So in this packet, you have all these discovers at once. And if you want to go back to a precise quotient, then consider a compact open subgroup of the finite adhers, which is just that. So for example, K could be just GLN of Z had the finite completion of Z, and then let me write it here. GLN mod out by K, and to be precise, but you can essentially forget about this today. This quotient is essentially x over gamma for some gamma. It's not quite true. It's only a finite union of such of x over gamma j. So it's a finite union. And in most of what I will say later, you can just consider the connected component of the identity in the left-hand side double quotient, and then it's really x over gamma. So just let me say what are the gamma j here, and what in fact you use strong approximation theorem to decompose GLN F as a disjoint union of GLN Q plus GJ K, where K is our compact open subgroup, and then gamma J is the image of the intersection of GLN Q plus with the conjugate of K by gamma J, and you take the image inside GLN R plus quotiented by the center. So that's how you recover. So in brief, you can think you can just think of the connected component of the identities, and GJ will be just the identity, and gamma will be the intersection of GLN Q with the compact open subgroup K. So that's the standard adelic quotient, another way to think of x over gamma. And the thing is that we don't work really with x over gamma, but we work with a fiber bundle over x over gamma, the fiber being a vector space. So to do that, I will add something more to our data. I will add denote by V a Q vector space of dimension n. And then instead of the group GLN, I will consider the group calligraphic G as the semi-direct product of GLN with V. And we will redo everything that I have said before with this Q algebraic group. And And so now what plays the role of a compact open subgroup inside in the calligraphic G? You will take a compact open subgroup on GLN of AF and a lattice in the finite Edel of, so let LF be a lattice. Equivalently, the intersection L with the Q point of V is a standard lattice. And again, K inside GLN AF, compact open. And you ask that it preserve the lattice LF. Then these two data give you calligraphic K, which is the semi-direct product of these, and this is a compact open subgroup in G of AF. So I will consider this compact open subgroup, and the thing now is that we can consider both things. First, what I will denote like this. So you have the it's completely analogous to what happened with GLN. You take the double quotient, but instead of putting G of A, I will enlarge a little bit. I will put GLN R semi-direct product, not with Rn, but with Cm, because I want to take Cn modulo a lattice and multiply with the finite Edel, and take on the other side the quotient by SON, the center, and the lattice. And similarly, we can just consider the quotient by K, meaning we just add we just quotient by the compact open subgroup on the right. So exactly. And both these quotients are group fiber bundle. And the fiber is precisely something of the sort Cn over L over the additive the GLN or GLN mod out by K. Okay, so again, the way you should think of that is just that this double quotient is just a finite union of X cross Cn mod lattices that depends on J, and here gamma J. So in particular, if you take K to be as above GLN of Z hat, the lattice L have to be V of Z hat, so Z hat to the N. Then the connected component of the identity is gamma mod out by, the quotient of X cross Cn model by gamma. So this is really the same object that we were considering before, except that now we distinguish the finite places from what happened at infinity. So
is there a notion of Chern classes for bundles over these adelic spaces?
Yeah, because it's
you can do it by restricting to each place, place by place, basically.
This is a finite union of this standard of bundle of that type. So if you forget about L, don't quotient by L, then you have CN bundle, complex vector bundle on the standard locally symmetric space. So you can speak of their chain classes.
No, thanks. I was talking about before the example.
Yeah, but I mean,
Is the
general construction is always of that type. Okay, it's always of that type. It's just a finite union of what you see in the example.
Thank you.
It's really more a language, but it's convenient to explain what I will say now. And now is precisely to talk about Schwarz functions and associated divisor. So now, let me say what the space of Schwarz function is. So it's the Schwarz function on the finite ideal points of the vector space. So such a Schwarz function, which I will usually denote as phi f to specify it's at the finite places. So it's a function with C value. I could consider values in Q, in Z, or okay. Let me consider C value for the moment. That is compactly supported and locally constant. So, in other words, it is periodic with respect to some lattice, and the support is contained in another lattice. So let me just give a few examples. The simplest one is to take the characteristic function of a lattice, let's say this lattice, okay? But you can translate the lattice. You can also take the characteristic function of a point, a vector. Let me, for example, take this point plus the lattice, and you can take finite linear combination of that kind of function, and that's essentially what is a finite Schwarz function. And once you have this finite Schwarz function, in fact, you can associate to it a divisor. A divisor, which I will denote d phi f. And let's suppose that, divisor in this, and if phi f is, let's say, k invariant and LF periodic, then in fact d phi f, and I will describe it like that, will be contained. I mean, if you can project it, and it will be it's an isomorphism. It projects onto the quotient that we have considered right now, where k is associated to capital K is associated to K and LF. So this is really this semi-direct product. So let me explain what is this divisor. Then this is exactly equal inside the union, the disjoint union. Remember that this quotient on the right is a disjoint union of standard quotient, and in fact this is all the points that you obtain like that. I should say it. And C are all the points, the rational points modulo the lattice Lj, such that phi f of Gj psi is non-zero. So, in other words, if you look only at the component at the identity, so the one in the disjoint union J, which corresponds to Gj equal the identity, what you are considering here is all the points that are in the support. I mean, the negative of the point, but it's purely technical. Negative of the points that are in the support of phi. Okay, so phi is invariant by some lattice, but there are a few points that are not in the lattice but in the support of phi. Their projection gives a collection of points, and that's exactly the divisor associated to d phi f. Okay, so support of phi f give you some divisor modulo the lattice point, the period lattice of phi f. So it's really a way of reformulating this divisor I already discussed sooner, and the fact is that, which is really a simple fact to check, but I will just admit it now, is that the degree of this divisor is 0 if and only if the average of phi f, so in other words, the Fourier transform of phi f evaluated at 0 is 0. So this topological aspect, this divisor degree, translates very well into a more, I would say, analytical but at finite place aspect in terms of Schwarz function. And once we have this data, we can now build adelic theta series, and that's what I will now do. Okay, so that's the next. My next goal is to describe adelic theta series, and then I will go back to the classical situation. You see why I want to really deal with that, is that because I want to do something, to associate something to any finite Schwarz function. So to any finite Schwarz function, we associate the tensor product of the Schwarz function, which was not really a Schwarz function, it was a Schwarz function with values in differential form, phi tilde, tensored phi f, and also, remember, we consider psi tilde, tensored phi f. And these, at infinity, it takes value in the differential form. So in the end, what you get is a differential form on S cross Cn. I should say S plus. I don't know why I call it S plus. With values in the Schwarz function on A. Since I have taken the tensor product, now it's really on A, because at infinity we had the Schwarz function on Rn, and here remember the invariance. It was invariant by GLN R tensor product Cn. So we have this differential form with values in Schwarz function and of respective degree 2n and 2n minus 1. So we have encoded in the Schwarz space all the way to with respect to which kind of lattice we want to average our forms. And now to really make the average, we will apply the so-called theta distribution. We apply the theta distribution, which is the analog in our setting of the evaluation at a point. But we don't want to evaluate at a point, we want to sum over the lattice. So the theta distribution is just the map from the whole Schwarz function to C which consists in summing over all the lattice points. And when I say lattice point here, it's all the rational point, but remember that the support of a Schwarz function is contained in a lattice. So in that way, if we apply this to phi m psi, we get theta phi and theta psi that are maps that go from the Schwarz function at finite places to the differential form on S cross Cn tensored with the smooth function on the finite del of J, A del of J. So I will explain more this. And this is, oh no, it's really, okay. I will explain what it means. Let's take, for example, phi. Maybe one of them, phi or psi. It's let's say, yeah. The most important for us later will be psi, but so let's consider phi. So theta phi is a function that will, so it will depend on, so first you evaluate it on a finite Schwarz function. So usually I put it here. And then you can evaluate also on a point in calligraphic G of AF, which is just a couple GF VF. And when you evaluate this, then you get a form on a differential form on S cross C, S cross Cn. And what is this, this expression? Is the average on all the Q points of the vector space of my form psi tilde evaluated at C times phi f of GF minus 1 C minus VF. It sounds a bit weird, but let's consider a simple case. Let's consider, for example, again, the case where phi f, let's say, is the characteristic function of the standard lattice VZ hat, and concentrate at the point, at the identity point. So let's consider also GF VF just to be the simple point, the identity and 0. Then what is the expression we get? T phi. I forgot I don't write GF VF and phi f. Is just the sum. Oh, sorry. Here it's a phi. It's just the sum over all the points in V of Q such that phi f of xi is equal is non-zero. But if phi f of xi is non-zero, it means that this belongs to the lattice. So in fact, you are just summing over Zn this point phi tilde of z. So what you are doing, you are averaging the form, and the invariance of our phi tilde. Remember that we had GV star of phi tilde of GW plus V is equal phi tilde of of W. So here, maybe I should better say psi here. And now if GV belongs to gamma semi-direct product L is Zn, then GV preserves the lattice. So in fact, the sum we are considering here is invariant under the semi-direct product. So theta phi is gamma invariant. Semi-direct product gamma L invariant. And so it descends, so it defines a differential form on the quotient S cross Cn mod lambda mod gamma. And in fact, we know exactly what is this differential form because phi tilde at 0 is just the term form, so it's dual to 0. But now if you average by z to the n, then it becomes the dual form to 0. So it's dual to the 0 section. So in that way, we get the form that is dual to the 0 section. So what is the general construct? What does give the general construction? In general, all these construction give you the following proposition. Theta phi of phi f is closed and represents the class of phi f, or the class of the divisor, if you want, in H2n GQ better to write it like that. G of LF relative to G of LF minus the divisor phi f. So it's really the oh no, sorry. I was a bit running too fast here. Sorry. So it represents, as I said above. No, I have to write down the. Sorry, I will explain this. So the quotient. I write it here. So the quotient of GLN R divided by S1 and LF. So again, so let me explain with word why what it means. Phi f represents some divisor, so some torsion section in this bundle here, in this group bundle here. And if you look what happened at the point 1, 0, then you get exactly the statement I have said here, that theta f is dual to the 0 section in this quotient above. And if phi f is not just the characteristic function of a lattice, but is a finite linear combination of characteristic function of lattices, then the right way to say it is that it represents the class of the divisor in that quotient. So that's really a reformulation of this, except that you authorize more complicated divisor than just the 0 section. So somehow we have find a differential form representative of what I have described in topological term in the first lecture. And now what we do with that, we will form an Eisenstein series and explain what it gives. So the advantage of working adelically is that now we are in the standard setting of Eisenstein series, except that we work with group calligraphic J instead of the standard reductive group. But all the construction then is really the same. We can define this Eisenstein series associated to both phi and a finite Schwarz function, which is given by some Mellin transform of the theta series. We pull back by multiplication in the fiber by R, multiply by R to the S. Here we evaluate on phi f, and we take the standard Mellin transform. And of course, similarly, we can consider ipsi similarly. And now it's really the same as usual Eisenstein series, except that it has values, not scalar value, but it has values in differential form. So it gives a meromorphic function of S with values in differential form on this big quotient. And again, minus the divisor. And the theorem, yeah.
What does the functional equation look like for this Eisenstein series? I mean, also, can you say a word about its analytic continuation? Is it?
Yeah. So that's the content of the theorem below. The functional equation. It's exactly the standard one with the so E of S will be equal to some standard factor with E of 1 minus S plus the Fourier transform of phi at 0 over some over S, and I mean there is a pole. There might be a pole at S and at 1 minus S, depending on the value of the Fourier transform of phi at 0 and at and the value of phi at 0. So it's really
and the gamma factors are
and there is the usual gamma factor. Yeah.
Nothing from the differential form side is coming. That's
no.
I mean
no.
That would be the new part.
Yeah, but I mean, there is nothing really deep coming from the differential form part, except that there is this Fourier transform of phi, which is a function with values in differential form. But somehow we don't need exactly the exact expression of the Fourier transform. The important thing is that these are Schwarz form. And that's the only thing we use to have a meromorphic continuation, is that it decreases fast at infinity, and so the only pole that we can get are at 0 and 1, and then you control it using the finite Schwarz function. So let me state the theorem, so the theorem is the following: is that ipsi S sorry, I start with ipsi phi f S as a meromorphic continuation, and with no pole at S equals 0, and what I will denote ipsi of phi f, which is really ipsi of phi f 0, is now a form of degree 2n minus 1 on this quotient here minus the divisor. It is closed, and it represents a cohomology class that lifts the class phi f above in the class of the divisor in the long exact sequence and so on. So we should come back to the very first lecture. We had this long exact sequence, except that it was not adelic, but it was exactly the same long exact sequence. It's x cross Cn mod lambda mod gamma. All these terms are of that type, and you erase some finite number, some finite some divisors that are now associated to finite Schwarz function, and we have a class that is a term class here that is dual to phi f, and the class of the Eisenstein series upside phi f belongs to that step, to that element in the long exact sequence. It's a closed form of degree 2n minus 1, and that defines the cohomology class here. And how do you should think of it here is precisely the average of eta with respect to the lattices corresponding to phi f. So this is here that there is the average of eta, and it lifts the term class here. So that gives our lift, and by construction, because you see it's here it's a Mellin transform. It comes from the integral from 0 to infinity from the multiplication by r in the fiber. So if you take at s equals 0, you see that it's invariant by multiplication by an integer. And so the form here, in fact, belongs to the part of the cohomology that I had denoted with a 1, that is invariant by multiplication by integer. So that's really our canonical lift that I discussed in the first lectures. And now it's a canonical lift which has a nice differential form representative. I should say one thing, that all this works well in the trigonometric setting, Cn mod Zn, but in the elliptic setting, there is something that should be added, and is that, in fact, this works only if the Fourier transform of phi vanishes at 0, of phi f vanishes at 0. This is needed to be able to have really a closed form. Here, you don't need it here because psi vanishes at 0 in that setting, but in general, you would need to impose that the Fourier transform of phi f vanishes at 0. And this corresponds to the condition that the degree of d phi f is equal to 0 that we had to impose in the elliptic setting. So that's the only difference between the elliptic setting and the trigonometric setting. So now we have this class, which you see wants to be a gamma equivariant class, but in the affine case, there was something crucial. It was to push the point to the boundary. So we would like to know, is it possible here to go to the boundary, and the relevant fact on that matter is when can we push in the direction of some flag. So in the direction of a flag W dot, the form E psi phi f restricted to some x cross kappa as the with kappa a compact subset of Cn over Lf, L phi f, minus d phi f extends to a closed form on the Tietz compactification cross kappa that vanishes at infinity, if instead of taking the average of phi f on the whole space, you take the average of phi f on the finite space W1 in the flag. So the smallest space in the flag, and it is constant equal to 0. So I cannot explain this condition. It's really you have to look at the constant term of the Eisenstein series to understand this condition. That's where it comes from. So I won't discuss it no more. But it gives a natural condition on the finite Schwarz space. So we introduce the following notation. This is all the finite Schwarz function that satisfies for any W that contains E1 that the integral of phi f is constant equal to 0 if you take the average on this finite and so under this condition you can push to some part of the boundary, namely all the flags that contains E1 or a translate of E1 by gamma, because in the end the Schwarz function will be gamma invariant. So these Schwarz functions have a special behavior at some particular cusp. And the typical example of such a Schwarz function is this one. You take all the characteristic function of the point of the M torsion point in the first coordinate, 0 on the other, plus the standard lattice, minus M. So you see if you take all the k here, if you average on the line generated by the first coordinate, then what you get m minus m equals 0. So this function is always it satisfies that this is constant equal to 0, and is not that it is gamma not of m invariant. You just have to it's invariant by the group that stabilize the first line modulo m, the line generated by the first coordinate modulo m. So that's typical Schwarz functions that are useful if you want to be able to extend your Eisenstein series to certain cusps. And once we have that, we can do everything as we have done in the affine case, except that we work with the Eisenstein series instead of the form eta. And so this leads to the equivariant class and the cocycle. And as I said, we do exactly the same as in the last lecture, because now we have an equivariant map that goes from the we could go for let us say it like that. So let's take phi f k invariant LF periodic and satisfy the, I mean, for the moment, I don't really need this condition. I will explain when I need it. So let's erase it. Then we have a map that goes from E gamma. Recall that gamma is a group associated to K cross Cn, and that goes to X cross Cn. And this map is just the same map as last time. You take a base point in X. Each time you have a K tuple of elements in gamma, you draw the geodesic simplex associated to this point. So it depends on the base point, but not and of the construction. But this gives a perfectly well-defined map that is gamma wedge L equivariant, and so you can now pull back the Eisenstein form. This gives you an equivariant form that represents a class which we have denoted so far this, and now it's associated to the divisor associated to phi f, and it's a gamma equivariant class of degree 2n-1 in this quotient. Minus the divisor. So we have found in that way a representative of this class. But all this comes from you see it's from Atelier construction, very homogeneous. So from this, it's really not hard to follow, for example, how the École operator acts and so on. I won't tell much about this, but this is quite easy to follow. And again, what is the next step is to erase hyperplane. So erasing hyperplanes, we know we can associate a class that I will still denote abusively in the same way, that now belongs to n-1 cohomology of with values in the meromorphic form of degree n in Cn mod lambda, mod L. So we have a whole, in fact, we have a whole family of such class, which depends on the finite Schwarz function. And the last thing to say is that if phi f moreover belongs to this space where we impose some condition at the cusp corresponding to E1, then it means that all the construction here we can redo by pushing to the boundary. And now we can compute a cocycle representative. By replacing the geodesic triangle inside the symmetric space by geodesic triangles that are formed of modular symbol, and on which it's very easy to integrate our forms, and that's because it's a bit long to write down the result of the computation. I will just show you a slide where it is, and to explain you where it comes from. So that's on. Okay, that's, remember that now I'm working with phi which satisfy this special condition to be sure that it can be extended to the part of the boundaries that corresponds to flags generated by E1. So let me now go to this. So you see, sorry, I need to see it also. You see the slide here. So again, I insist phi f satisfies this special condition. To have a statement, a simple statement, I have fixed the lattice, so I ask that it is Zn periodic, and that it is invariant by a subgroup that in fact belongs to GL and Z. Then we can write down an explicit cocycle that is really a linear combination of n-fold product of forms that are cotangent function times dz. Okay, so you see each Lj is a linear form on C to the n. The xi j are rational points, and the coefficient of the linear decomposition involve this finite Schwarz function that is related to the divisor we are considering. And the theorem tells us that this explicit cocycle that is computed by pushing the point up to infinity is an explicit representative of the cohomology class I have been discussing from the very beginning, namely there is a but it's, of course, it's because sometimes I call it multiplicative, sometimes trigonometric cocycle. So it's the trigonometric cocycle associated to this special divisor. But what makes me happy, of course, is that it is now it makes relation between n-fold product of these meromorphic forms that are governed by homology class in gamma. But now remember that in fact we can go to part of the boundary of gamma. So in fact, this is more than just a cocycle like that. It's really a map from partial modular symbols to meromorphic forms. So let's look at the example to conclude. Almost, let's look at the example where phi f is the example is the function I have mentioned earlier, meaning the sum of the characteristic function of k over m 0, 0 plus z hat minus m characteristic function of the lattice. So this is maybe the simplest function that satisfies this condition. And then let's look at the map that we can construct using this. Then the building block, if you want if you have n vectors or just a matrix with integral coordinates, so the matrix that I denote H here, let's say that it's invertible in Q, then we can associate a product of cotangent function. For example, if the matrix were in SL and Z, then it will really be just a product of cotangent function, this C of H. And now from this, I build a map. When you take n vectors v1, vn, I associate this, so first this form, C of v1, vn, multiplied by m, and here vi prime is the same as vi, except that vi, I will stick to elements that are congruent to something here and 0, 0 here mod m. And so vi prime is the same vector where I divided the last n-1 entries by m. Okay, so vi prime is v11, and then v21 divided by m, and so on, vn1. Sorry. Okay, you can divide by m the last coordinate, because I restrict to modular symbols that are associated to the special flag that are in the orbit generated by vector in the orbit of E1 by gamma naught of M. So these are exactly this type of vectors. And now on this partial modular symbol, I have this this expression where pi m is just this map. And so we have, if you want, we have smoothed the naive expression. There could be a naive way to build the map from modular symbol to project of cotangent function. That would be just to take the to take this kind of product. But this naive way would not give a cocycle. But what we can do is just take a smoothing associated to this to this partial modular symbol, and you have and now it really defines a cocycle. That is the cocycle we have considered up to now, namely namely the cocycle associated to the special phi f I had mentioned. So in the end, that's what I wanted the story I wanted to tell. You start really from purely topological stuff, and in the end, this gives an explanation of map that really looks like the Sharifi map or that kind of a quite surprising map. But now they really come from the topology, and in particular, we never use. Maybe I've said that we never use anywhere that we never decompose a modular symbol into unimodular symbols. It really comes from the topology, so we don't have to use that there is some Manin theorem or something like that, and this can applies for in situation where the field is not Euclidean, and we don't for example that kind of stuff. And yeah, maybe it's if you ask me, I can just show you a slide in the elliptic case, which and that's all. I will stop here for today and for the week, and thanks for listening me up to now.
I want to thank Nicolas for this wonderful series of lectures, in particular for today's talk. So are there any questions or comments?
Small question. Are these partial modular symbols preserved under the action of Hecke operators?
Yeah, so yeah, I should say that yeah, there is you can write down exactly how the Hecke operators acts on these. Yeah.
And they take a partial modular symbol to a partial modular symbol.
Yeah.
That's the okay. So in a naive,
I mean, the Hecke operator corresponding to the group gamma naught of M.
yeah, of course. Okay. And a naive comment in physics these days, there's this thing that's become really popular called the Siegel-Way formula, which is very similar or reminiscent to what you're doing, where you average theta functions, but that's all in the classical language, that you're just averaging theta functions over Siegel moduli spaces. So do you see any similarity, or?
I mean, I don't know exactly how to answer your question, but the Siegel-Way formula should, yeah, I mean, of course there is similarity. I mean, that's the way I kind of think.
Can one think of this as a generalization of the Siegel-Way formula to vector bundle case, or?
No, I don't see it like that. No, but maybe no, I don't see it like that. But what I was. I think the Siegel-Way formula could be very useful in that in that setting for the following reason: is that all this, I mean, when you specialize to yeah, when you specialize to some points, you go back to classical situation when you have a really the standard Eisenstein series and lift and standard theta lift, and the Siegel-Weyl formula could be helpful to show you that some natural lift to meromorphic form, or if you dream, you could even dream to have such lift to higher K-theory group, and then maybe the Siegel-Weyl formula could be used to prove that some K-theory classes are non-zero through their regulators. But that's something I would like to pursue at some point. But yeah, but I don't know exactly what answer you
Thank you. That was a great answer.
Are there any other questions? So maybe I can ask you, Nicolas, if you can, so these things that you were saying at the very end about your motivation, and you kind of mentioned a slide that you haven't shown us on the elliptic cocycles.
Yeah, no, I just want, and maybe Pierre will mention some related thing, except that it will not be exactly the same setting as I understand. But I just wanted to say that all I have said, now that we have all the machinery, it translates immediately in elliptic setting, and so you just have to replace the cotangent function by a theta function. The only thing is that you still have to have a degree 0 divisor. So in some sense, you have to add some kind of smoothing on the other side, on the toe side. That's why the cotangent function can be, one way is to replace the cotangent function by this function I denoted that are usually denoted theta c here, that are really periodic by a lattice, because the theta function is not it's not Z2 periodic in Z. But now if you smooth it a little bit like that, then it becomes really a periodic function, and all I have said before translates in the same way. Yeah, so you have a partial modular symbol here, which really takes the same formula, except that now you replace cotangent function by d log of theta as in this formula. So now you have a partial modular symbol like that, and it defines a cohomology class of degree n-1 that I want to call the elliptic cocycle with values in meromorphic form on product of an elliptic curve, and which are very, very explicit. I mean, it's really product of us. So in some sense, it's I like to think of it as something close to Kato systems of units in the GL2 situation, because in GL2 case it's very related. We don't go up to the units in that case, but I mean, there is a common generalization on both that is somehow contained in Sharifi's talk in the GL2 case, because two regulators can go either to the units or to the meromorphic forms. In the GLN case, we have something like that for in any degree for meromorphic form, and we understand the relation, how the École operators acts on this. So the formula is a bit complicated because for GLN you have n-1 École operators, but and this one is the École operators on these groups, and the TP are the usual École operators on the tau variables. Because here it's meromorphic form on the universal elliptic curve to the end, so there is both a z and a tau variable, and the standard TP are the standard École operator on the tau variable. So, and now you can play many games. I mean, you can evaluate on a torsion point, you can evaluate at a CM point, and then you go to Lewis talk, because and so on. So that's then you.
Yeah. So the great advantage of this construction is it gives a unified viewpoint, indeed, on many different constructions of cocycles that lead to information about rationality, integrality of special values of L functions, and so on and so forth. Do you see what could be new theorems that you can prove using this structure? I mean, is this sort of, because of course it's very beautiful in its own right. I mean, and it has
no. That's a completely fair question, because that's I mean, as I said, I like this relation between cotangent function or between theta function, because it makes structure in some world I wanted to understand, but somehow it's a bit deceptive, because it's not yet clear what really new deep theorem you can get from that. So Lewis mentioned one type of theorem, but that you can decompose these special value. Not only the special value are algebraic, because I should say that algebraicity is you don't have to fight so much to have algebraicity. You don't have to push until the boundary. Why would you do that? I mean, you have a perfectly nice class in meromorphic form. You evaluate and then you have algebraicity. What you gain here is really to decompose into products of functions that are that exist in dimension 1, and that's what I find surprising and nice is this product. But now your question is perfectly is a very good question. So what next? What do you do with this product? And yeah, for the moment we do some nice stuff as what we did with Louis. We have, but it's not so clear if it's a very if what to do beyond that. There is one thing related to K-theory that we are pursuing, but yeah, it's not so clear. I mean, it produces a lot of cohomological, very explicit cohomology class that can be yeah, but what's next is not so clear.
I mean, it could also be maybe applications outside of number theory. I don't know. Do you think that this could lead to interesting geometric or topological?
Yeah, I mean, what's intriguing also in the but I don't think it will follow. Yeah, no, I don't know. I mean, in the additive case, as I said, it gives a nice proof of a nice relation for the Solomon algebra, but it's not something new. It just, you understand it more topologically. I feel I understand where it comes from, but as soon as you average, you are really looking at. I mean, what it says is that structure of complicated algebra of meromorphic forms can be a little bit understood using modular symbol or partial modular symbol of SLNZ. Mm-hmm. So you are really in the, I think, in the arithmetic setting. The next question is, I mean, one natural question that I'm sure you have in mind is, what about evaluating at not only at torsion point, but at real quadratic point, for example? That would be nice. That's something I like to explore, but for the moment, it's we are not there yet. That's.
So I wonder if there may not be some connection with sort of Arithmetic theory. In other words, you're really working on these Kubasato varieties here in some sense. You have the modular curve in the elliptic case. You have your modular curve and on the base, and then many copies of the elliptic curve giving you this torus bundle that you're working on above that, and maybe you're taking out some sections and so on. And really what you're doing is something at infinity. But of course, if you took that whole picture and made an integral model of it, and looked at cycles there, you know, of course, in Arithmetic theory, you would then want to define classes in Arithmetic Chow groups or Gillet-Soulet Chow groups. And of course, one big and most maybe difficult part of those things, the cycle part is just what it is, would be to establish nice green currents or green functions for green currents in general, because these have higher codimension, green currents for these cycles. And I wonder if your machinery could have some applications there. In other words, obviously you've done something more subtle where you've taken out hyperplanes and you're looking at the boundary, et cetera, but still one could ask if, what would be needed to do an Arkelov theory type application, what would be needed to try to make green currents for such cycles in these Kugasato varieties and study their behavior, and maybe your cocycles actually are related to that.
Yeah, yeah, maybe. I mean, the multi-equivalent form are really the right object,
Absolutely.
I think, to
Absolutely right.
do that. And yeah, no, that's something. Of course, Luis is really in
Sure. Of course, he's an expert in this area.
Knows a lot about this, so it will be better to answer your what you say. But I'm not sure he's here. But
it's not really a question so much as it is a suggestion that maybe there's some nice connection there. I mean, that's somehow the point.
Yeah, that's. But again, the funny thing in this story that I have only slightly touched is to go from the multi-equivalent forms that are really real forms and to holomorphic forms.
Yeah, no, this is very interesting, and I wonder also if maybe that has a more general application. In other words, that's a new aspect that you're introducing, and maybe if we go back to more classical questions about green currents and Arkelov theory, maybe this kind of a construction has some relevance there, right? In other words, it cuts both ways, you see. So that might be an interesting thing to pursue from on that side with the sort of standard constructions we know already. But maybe this viewpoint is a nice thing. Right?
Yes, thank you. Yeah.
Are there any other questions or remarks or comments?
Yes, sorry. Could I ask a question?
Yeah.
So for just one point of clarification, so this elliptic cocycle that you define at the end, the equivariant one, this is one that you kind of mentioned yesterday, requires some sort of like argument based on the results from Clément-Dupin's thesis, where you
in fact, both the trigonometric and the elliptic require this. Because what the multi-equivalent form give you is an explicit cocycle with values in differential forms on the fiber, on Cn minus on the fiber minus hyperplanes. So in the trigonometric case, it's C star to the n minus some hyperplanes, and in the elliptic case, it's E to the n minus some elliptic hyperplanes. Mm-hmm. Okay, but the multi-equivalent formalism give you real forms that are in fact just the real part of the meromorphic form that we want to understand, namely a cotangent function in the case of in the multiplicative case, and theta function in the elliptic case. Mm. And to go from relation between the real part to relation between these forms, you have to say that the cohomology, the map in cohomology from a meromorphic form to the cohomology is in fact an isomorphism. Mm-hmm. And that's precisely what we need to prove in the, in the additive case, it's just the Briscoe theorem. Yeah. In the trigonometric case and elliptic case, it's something we need to prove. We don't prove it for the whole cohomology. We prove it only for a small part of the cohomology, the one that is invariant by pushed forward by integers.
Okay, right, that makes sense. Yeah. Okay, cool. And then I guess my main question was, could you clarify a little bit the relationship between these like last constructions, especially the elliptic one, I guess, and the Eisenstein theta lift that you talked about in the Takagi notes? Like, does this give a somewhat distinct approach to?
Yeah. So. Yeah. So it's like the constant term of the in what I've said during the week, we started from a class that is of degree 2n-1. I mean, the equivalent class is of degree 2n-1. In the Takagi notes, the class is of degree n-1. But it is scalar value. And so to go from the 2n-1 class to the n-1, you consider the term that is I mean, sorry. So what I've said today, you get a n-1 cohomology class of the group with values in degree n forms.
Yeah.
And now you can consider, you can kill the part that is in front the standard degree n form, dz1 up to dzn. Okay. Then you get and you evaluate at a torsion. When you evaluate at a torsion point, you just get a number.
I see.
And this class is the class that is considered in the Takagi notes.
Oh, that makes complete sense. Okay.
Okay, but
this
yeah.
isn't really about the theta. Like I thought maybe there was, because the 2n-1, there was maybe a relationship between the with the GL2 comma GLN theta lift.
No, but yeah, exactly. So sorry, let me just draw a picture to explain. So you have in what I have said today, you have GLN, and you have a theta lift to GL2. But you see this only after you evaluate at a torsion point, because what we have is a class. So let me say consider the elliptic class. So it depends on the divisor, and it belongs to h-1 gamma with values in meromorphic form degree n on the universal elliptic curve to the n. Okay. Now here I can evaluate at a torsion point. So you have to, of course, you have to be precise on where to take the torsion point, but I tell you that you can evaluate somewhere. There are some torsion points where you can evaluate, and then what you get then is a cohomology class with values in the meromorphic modular weight n modular form on the curve. So if E is above E to the n is above n is above a modular curve y, then pulling back a meromorphic form on E to the n at a torsion point give you some modular form on the tau parameter.
Yeah.
Of
Okay.
weight n. Okay.
Right.
So you have this. So
Yeah.
it means that when you cut this map with the cohomological representation of degree n-1 of GLN, then you get a weight n modular form. And that's exactly what the theta lift. I mean, if here you have a cohomological representation of degree n-1, then theta of pi is a weight n modular form.
Yeah, no, that makes complete sense. I was being really stupid because I thought I didn't realize that you could plug in that like it was meromorphic forms in the universal elliptic curve, because earlier it was like it looked like this n on like C mod Z or something like that.
And in fact, you can. That's why you can. I mean, there should be some interesting number theoretical thing to do, because you can also take Peterson. Here you can take Peterson product with a cusp form, for example, and then then you have integral model. You have some kind of integral model of the theta lift. That's something certainly which should be investigated. And since it's your fault, okay, since you let me talk more, then I will finish this and explain using I am a big fan. I don't know if Stephen Kudla is still here, but I am a big fan of the CISO philosophy of Kudla, and so here what I was describing is a theta lift from GLN to GL2, and now you can restrict to there is another dual pair here, which is GL1K, you embed an imaginary quadratic field into Q as a CM point, if you want. And here you embed GLNQ inside GLNK. And when we do that, what does it mean geometrically? It means that you restrict the modular form, you evaluate, sorry, the modular form at a CM point. And so, and what happened is that in fact, the class you get is related to the class you would have by you get looking at this diagonal, which is the cohomology class of degree n-1 of a Bianchi group with scalar value. And so the CISO tells you that if you evaluate on the homology class in GLQ this class, then in fact you get the value you get is the specialization as a CM point of a certain modular form. So you can play several games like that. So I will stop here because I don't want to play alone. But
am I allowed to ask another question, or am I pushing the time too much? Okay. With your construction so far, do you already have control of like can you get the values of the meromorphic forms on a universal elliptic curve to be like algebraic or rational with what you have so far?
Sorry, say it again. The values of what?
Like, can you get I guess can you get like a cocycle with values in like modular forms with like rational Q expansions or something like this? Like, do you have like is it the wrong construction, or can you actually make it algebraic like that?
Yeah, I mean, yes, at that level, yes. We haven't written it, but somehow, but this, I should say, this should follow also. Let me think. Yeah, that's interesting because that's precisely where I think the approach of Johannes and our come to intersect, and to get algebraic results at that level, my opinion is that somehow what Johannes Preng has described to us is more powerful. But yes, the cocycle you get here in the, will be almost integral if you put integral structure everywhere.
But does that follow from things you've already said, I guess, or is there more to the story?
It's essentially follow because okay, you have to follow the map that goes from this meromorphic form on the product of elliptic curve to the modular form. So, so it's essentially follow from what. But we haven't written this, and I don't think we will ever do it because I really think that the right viewpoint, if you want to go there, the viewpoint that that Johannes has described is more powerful because it really comes from the motivic from a motivic class. So it's what would you expect more? But what I don't think you can get from this motivic class that Johannes described is what we get by pushing to the boundary. I mean, all this map, Sharifi type maps or Kato types map, I think there is a lot of work. There is a lot of interesting work to do in that direction too, because so for example, if you wanted to have some kind of, I mean, the map Goncharov described or the map Bruno described by using explicit map from modular symbols to K-theory, there should be obtained by some procedure like that, by pushing to the boundary the class of that Johannes has described, but the difference is that Johannes does not work with trivial coefficients, so they work with the polylog. So I don't know exactly how to. I don't know how to reconcile this, but maybe Johannes have some viewpoint on that. I don't know.
Okay. All right. Thank you. Yeah, that's really enlightening.
Okay. Well, I want to again thank again Nicolas for his entire series of lecture. Maybe propose another round of applause for his talks, which were greatly appreciated.